Okay, so welcome everybody. Thanks for being there, joining this almost weekly meeting of the Quantum Spain seminar series. So this week it's a pleasure to greet Lluis Masanes. Let me say Lluis Masanes correctly. So he has accepted to give us an overview of his work, which is quite technical but very exciting. I find it really suggesting. So let me introduce him briefly. Luis made his PhD in Universidad de Barcelona with José Ignacio Latorre. And then he moved to make a postdoc in University of Bristol. He's now associate professor at the University College in London. And he's specialized in topics of in quantum thermodynamics, quantum open systems, tensor networks, and all that. So he's going to report on this fascinating field of the self-dual unitary circuits. And please, Luis, the floor is yours, and thank you very much.
Thank you so much for this presentation. Thank you, everybody. Buenas tardes. Okay, so so I want to give an overview about conformal, what I call conformal circuits. It's a new thing, and how they can be used in a version of holography, of theories of quantum gravity that I call discrete holography. Okay, so first let me just give an overview of why to use unitary circuits in quantum many-body systems. Okay, so what is the type of model that we are looking at? So the best is to think of a spin chain. Okay, so this is, sorry, can I, no? Having problems with my pen. So consider a spin chain. Yeah, okay, good. We have a spin chain. So each spin has dimension q. Okay, and this is what people call a brickwork circuit. Okay, so U is a unitary acting on two sides, and V is a different unitary acting on two sides. And so if you put an evolution operator in this way, you can write a system that is translation invariant in space and in time. Okay, well, it's translation invariant every two sides. Okay, so this is so the dynamics of, if we just take a local operator, let's put a local operator and see how this evolves. After each time step, its support can in principle grow up to here from the right and to the left here. Okay, so it automatically, just because of the structure of the circuit of the evolution operator, it has a strict causality. Okay, so by the way, please interrupt me with any questions. I think it's much more fun. So for instance, if we consider a Hamiltonian with local interactions, this strict causality is not true. Okay, so we have Lieb-Robinson bounds, but beyond the light cone, we have exponential tails. Okay, so in some sense, circuits are more similar to quantum field theories in the sense that space-time plays the same role and that causality is strict. Okay. Also, because of the structure of another just property of the fact that we are dealing with circuits and not with local Hamiltonians is that we don't have any locally conserved quantity, energy or any other in general. Okay, so if we have a local Hamiltonian, automatically energy is conserved, of course, and energy is a local quantity, a density, if the Hamiltonian is local. However, here you can consider this, the evolution operator, the one layer of the evolution operator, of course, commutes with itself. Okay, so you can consider it to be a conserved quantity, but is not of local type. Okay, this implies that thermalization will have a stronger form. So circuits in general, there are exceptions, have a stronger form of thermalization, stronger form of quantum chaos, scrambling, and all these things. Okay. Another feature of quantum circuits is that, this is our single-step evolution operator, okay? And unitaries, the eigenvalues of a unitary are complex phases. But you could imagine that the analog of the energy is the phase. So what has to be the exponent of the imaginary exponent of the exponential, so that it gives these complex phases that are the eigenvalues of u. So, but complex phases, we cannot order them, because if you take a complex phase and add 2 pi or any multiple of 2 pi, although you get a different number, it's going to be the same complex phase. So when you deal with complex phase, it's not possible to order. You don't have the smallest eigenvalue, the largest eigenvalue. So in particular, we don't have a ground state. Okay, and we can also not construct thermal states. Okay, because the only thermal state that we can construct is that of infinite temperature, which is the maximally mixed state. Okay, we could put q to the power of L. L is a number of spins. So these systems, when they thermalize in the strong sense, in the sense that locally, even if we start with a pure state, after some time, if we look at any region of the spin chain or any sufficiently small region, the reduced density matrix looks like the maximally mixed state. Okay, so this is why they thermalize in a stronger sense.
Can I ask a question, Luis?
Yes, please.
So it's important to have two U and V, two different.
No.
Basic.
You could put U and U could be the same as V. You could also consider systems with disorder. Okay. For instance, in my last bullet point, I'm saying that circuits displays a range of phenomenon, thermalization, many body localization. Of course, if you want localization, you need disorder. This means that this is going to be U1, U2, U3, U4, U5, okay? But you can choose. You can make them all different, all the same. And soon when I go to the conformal circuits, I will specify what is U, what is V, and so on, okay?
Thank you.
So quantum chaos, hydrodynamics, these are all phenomena that you can find both in local Hamiltonians and in causal circuits, okay? Okay, so now, so this was in general about quantum circuits. Now I want to talk about what are, let's say, my contributions, okay? The new ideas that I'm presenting in this talk, okay? So the first is I'm going to introduce a family of circuits. So in the mathematical physics literature, when you have a translational invariant circuit like this, you call it a quantum cellular automata. This is a strange name, but it comes from, from computer science and von Neumann and the definition of classical cellular automata, okay? For me, if I had to put the name, I would just call it a discrete quantum field theory, okay? For me, this is a discrete quantum field theory, okay? Where both space and time are discrete. So when people talk about lattice field theory, then space is discrete, but not time, okay? And here everything is discrete, okay? So I'm going to introduce, I'm going to specify what are these unitaries, and it will be chosen so that this lattice model has a discrete version of conformal symmetry, okay? So we are going to see this. The second idea that I'm going to introduce is that I'm going to use these unitaries, but here these unitaries are used to construct the evolution operator. This is a single time step evolution operator, but I'm going to use these unitaries to construct tensor-network states, okay? So this is a tensor-network state for a spin chain of 20 spins, okay? Because every tensor, every two-side unitary has all legs contracted except for the ones in the boundary, okay? So this tensor network specifies a pure state for 20 spins, okay? And you can imagine constructing different tensor networks for any number of spins, okay? Q, as I said before, Q is the local spin dimension, and you have to put this to get this normalized state. We will see this. And what's the point of defining these tensor network states with the same, it's a bit weird to use unitaries to define a state, okay? Well, it's not, it's sometimes used, like in MERA, in the multiscale entanglement normalization ansatz, but here we do something different. But the reason that we find this interesting is that now, if so I can, of course, I can interpret this tensor network as a discrete geometry, okay? This case would be flat Euclidean geometry with some square boundary. But now I can apply the evolution operator to this spin chain, okay? So you have to imagine that to each of these spins, it acts one of these legs, okay? So you put it, it looks like a corral, no? Like this would be like the fence of the corral, okay? So, and when you act with this evolution operator to this state, then you get a different tensor network state, okay? So with this type of states that have the same unitaries as the dynamics, the nice thing is that one tensor network state evolves into another tensor network state. So you have a dynamics of discrete geometries, okay? So, and we will see later that these dynamics has lots of features of gravity, of classical general relativity, or not, let me say, not lots of features, but some features, okay? We will also say that these geometries satisfy the Ryu-Takianagi relationship between entanglement and geometry. So I'll explain this later, but this means that the geometry of this tensor network state is related to the entanglement of this quantum state of the spin chain. Any question? And yeah, and finally, I will conclude that by using this formalism, we can, these discrete geometries, we can see, we can observe some gravitational phenomena, okay? Like time dilation, gravitational time dilation, black hole formation, and growth of the black hole throat, okay? So now let me introduce this family of circuits that I call conformal. But before this, I need to introduce what are dual unitaries, okay? So this is going to be my notation, okay? This is a unitary acting on two spins. These are the two input spins and the two output spins. I put the arrow pointing towards the future because I'm going to consider variants of this tensor. Like for instance, its transpose. Its transpose is just take the tensor and flap it down, okay? This is the conjugation with the swap operator. So because I'm swapping the two spins, then the arrow in the left moves to the right. Okay, and complex conjugation, I just put a darker shade. Okay, so because this is a unitary, it must satisfy the unitary condition, which written in this language amounts to this. Okay, so if I apply to U this U, which is both transpose and conjugate, so I have dagger, I have to get the identity. This is the identity in tensor network language. And this is the other condition for unitary. Well, they are equivalent, you know. So you can understand the standard condition of unitarity as unitarity in time, because time goes vertically, okay? So with this in mind, you can define also unitarity in the space direction, which is I take the original unitary and apply this, let's say, spatial dagger. It's spatial dagger because instead of doing this, I'm doing this type of conjugation, okay? So I just, which is basically swapping, applying the swap operator between the left and right spin, okay? And of course, complex conjugation. So these U and U with spatial dagger, if I contract them, I have this sort of spatial identities, one for each spin. Okay. So any questions about this notation? Okay. Now, let us see, what does, so we all know this constraint, unitarity. We are very familiar with that. But now, let me explain what this extra constraint imposes. Okay. Well, let me uptake this unitary and transform a local operator on the spin of the left. Okay. So in general, for any unitary, you will get this. You will get that if the unitary acts on an operator localized on the left, in general, you will get a linear combination of something on the left, something on the right, and something with non-trivial support on both sides. But now, if I impose that U is dual unitary, it satisfies these two constraints, then this term is never present. Okay? So we can understand this fact as the fact that something on the left moves to something that always has non-trivial support on the right. This has non-trivial support on the right, and this also has non-trivial support on the right. In the left, this still has trivial support in the left. But so visually, we can imagine that if we have a spin in the left, it will move to something that will have non-trivial support on the right, and this will move to something that has non-trivial support on the right, and this will move to something that has non-trivial support on the right, and so on. The support inside the light cone can be simple or can be very complex. In general, it will be a large superposition of terms, a large linear combination of terms, but all these terms have non-trivial support on the right edge of the light cone. And if instead of starting on the left, we start on the right of the original gate, it happens the other way around, okay? So it moves non-trivially to the left, okay? So things, local perturbations move at the speed of light in dual unitaries circuits, okay? Okay, so this is, maybe I can explain this here. So, sorry, no, I want to go backwards. No, how I go backwards? Yeah. Okay, so this is in general what you get with a dual unitary, okay, this linear combination. But for some dual unitaries, it could be, or for some initial operators A, it could be that this is not present, okay? So in this case, A is mapped to another local operator shifted to the right, okay? And it could be that this A is mapped to something, it could be that C is proportional to A, okay? If this happens, we say that we have a free particle, because basically this operator at site X is mapped to the same operator at site X plus 2, okay? Or X minus 2, depending on if it's on the left leg or the right leg of the dual unitary, okay? So these are free particles that don't interact with each other. This is the associate phase, okay? So if you give me a dual unitary circuit, okay, if you give me this, I can construct this completely positive map, and I can find, and this different one, and I can find the eigenvalues of each of the two maps, eigenvalues and eigenvectors. The eigenvalues that have unit modulus correspond to these free particles, and the eigenvalues that have modulus smaller than 1 correspond to quantum chaos. Maybe the only thing that I can say is that because you have this term, sorry, because you have this term, this part will make the thing spreading in both directions, and the operator just grows and grows and grows, okay? So this is just an intuition of why it gives us quantum chaos. Okay. Any question? Okay, so now let me be more concrete, and I'm going to introduce, so I have introduced what are dual unitaries, and now I'm going to tell you how you need to arrange dual unitaries to construct a quantum circuit that has conformal symmetry. Okay, so you give me this dual unitary, and then once you have given me this, all the others are just rearrangements of the original one. For instance, this is just taking the original one and turning it upside down 180 degrees. This one is a different rotation and it's complex conjugation. And you know, this is done so that this is facing itself in this direction. This is also facing itself in this direction. This is also facing itself in this direction. This is also facing itself. Okay, so you see kind of a symmetry from every right angle. So this is how, if you put this gate, you automatically know how to put all the other gates of the circuit, okay? And now you can ask, okay, but why this particular structure, okay? Okay, so in order to answer this question, let me define the dilation operator, okay? So the dilation operator is also constructed with the same dual unitary gates, but it maps, this is the structure, okay? It maps a spin chain of n sides to a spin chain of 2 n sides, okay? So you can see that here there are twice as many legs as here, okay? And why we do this definition? Okay, because if I apply this dilation isometry to the evolution operator, now I can apply the conditions of dual unitarity. For example, this is the inverse of this, okay? Is the dagger. So these two gates, these two boxes can be replaced by the two identities, 1 and 2, okay? And the same here. I can replace these two gates with these two identities. So basically, I'm using this condition that I have, these conditions, okay? It's just that instead of being this way, the gates are this way, but that's irrelevant, right? Okay, any question? So we can keep on proceeding with the contraction. Now we can, here we also see that these two are, one is a dagger of the other. So I can contract this, and later I can contract this, substitute it with two identities. This long leg can be just moved down. And yeah, I can also eliminate these two, okay? So at the end, I just, I get the evolution operator on the shorter spin chain, and again, this dilation isometry, okay? And of course, this repeats itself. Here you can see that again, you have this structure again, okay? So maybe we can summarize this relation in the following way, okay? So if the evolution operator on a spin chain of size 2n, and yeah, sorry, I have to say something. This is not the evolution operator, but half of the evolution operator, okay? But if you apply with two times, if you again apply another copy of this evolution operator on top, you will get a full evolution operator in the other side. So this is the exponent. Two copies of the evolution operator on the left give one copy, commute to one copy of the evolution operator on the right, okay? And as I said before, on the right there are n spins, here there are n spins, and in the left or in the top, there are two n spins. Okay, so we see that the dilation operator just dilates space and time by a factor of 2. Okay. So yeah, it's the fact that we are using dual unitaries and that we are constructing this spatial structure so that we can do all these algebraic tricks. Okay. Questions? So we can say that this family of models, each of these models, form an exact renormalization group fixed point. Okay. Okay. So now I'm going to just change a bit the notation to save space, and I'm going to redefine each block of these gates by a single block. Okay. So these two legs, now I write them as a single leg. So if these legs have dimension q, now this leg will have dimension q square. Okay. And yeah, so now the previous circuit, now it looks like this. And this is the reason I have done this redefinition. Okay, so that it looks simpler. Okay, so now what I want to do is to convince you that, so we have seen that this circuit is, or if you want, the previous circuit is scale invariant, okay? Because after it commutes with the dilation operator, is itself with a spin chain of a different size, twice as large or twice as small, okay? But I want to show that in addition to dilations, the symmetry is the full conformal group, also Lorentz transformations and everything, okay? So now what we are going to do is I'm going to tell you what is the conformal group in the 1+1 case. Let me define this, okay? So now we go back to the continuum, okay? So now our coordinates are, if you want, this is space and time, okay? 0 and 1, space and time. So it's R2, okay? Now, so let us consider all transformations from x0 to x1 to z0 to z1 that when I transform the metric tensor stays invariant up to a proportionality factor that is positive, strictly positive, okay? And of course, this proportionality factor can depend on the location, on the point. But apart from this, this has the same structure and this, okay? So, and this is the, if you know about differential geometry, this is the rule of how you change the metric tensor when you change, or any tensor, when you change coordinates, okay? So this is a general change of coordinates, and then conformal implies that it has to be of this form, okay? So now, this is not a very difficult problem, and if you solve this problem, the solution is very simple. To express the solution, I need to define the light coordinates, okay? So maybe let me write, so these are the standard coordinates. And these are the light coordinates. Okay. So once we express everything in the light coordinates, okay, so I define for the initial point and the final point, I define, instead of 0, 1, I will define the plus and minus coordinates, okay? So once you write the origin and the destiny of the transformation in light coordinates, then conformal transformations are this simple transformation. You just independently transform the plus coordinate to the plus coordinate, and independently the minus coordinate to the minus coordinate. Okay, so it's really simple. And f can be any function with strictly positive derivative. And g the same, any function with strictly positive derivative. Okay. Any question? A long silence, okay? Okay, so with dual unitaries, one second. Okay, I'll continue. So with the same dual unitaries that we constructed the dynamics, the evolution operator, we can construct this operator. It's another operator. In principle, is defined in the infinite chain. So what I'm going to give you is the generators of the conformal group in the infinite chain. If you consider finite chains, maybe this changes the situation, okay? And we can see that when you add to a local operator, at the left of, so this is, X is any location in space, okay? So at the left of X, this operator acts like the identity. So maybe let me write at the origin as 0 time. So this, if you have a local operator here and this acts on it, nothing happens, okay? But if the operator is in the right of the X, then it will move to the future and to the left, which are these arrows, okay? To the future and to the left, northwest, let's say. Okay, and you can construct other transformations. This at the right of X is the identity, and the left of X moves to the left and to the future as well. So you have this, okay? Now I'm only justifying the arrows, this transformation at the origin, okay? I'm not talking what happens in the future and on the past, okay? Later I will justify this, okay? But at least on the origin, at least at this line, if you put a local operator at any point on this line and apply and conjugate it with these group elements of the conformal group, here it will be translated to the left and to the future, and here nothing will happen, okay? These are other types of transformation. So we have these 4. So the previous ones, 1, 2, 3, 4, and the corresponding daggers that do the inverse, okay? So if I put a dagger here, I will get identity here, and here the arrows will go the other way around, okay? Now, let's go back to justify the action of this operator for local operators that are not in the present. They are in the future or in the past, okay? To do so, I consider a local operator and translate it to the future or to the past, t units of time, okay? Small t. Big T is the evolution operator for one time step, okay? And now you can apply a similar thing as before. So I just, this is just, sorry, there is a mistake here. This Jx should be called C minus X, okay? The mixture of notations. So if I apply this to from the left to the evolution operator, this is the inverse of this. I can transform these 2 gates into 2 identities. Now this is the inverse of this. I can transform these 2 gates into 2 identities. And then here we can see that this is the same as this. I'm just rearranging the gates, but no contraction has been made. We can see that now this is the evolution operator. This is C minus or J here. But now, if you look here, J is located, it starts at X, this is X, and now is 2 sides to the right. So when you commute T and J or C, it moves to the right, okay? And this justifies this diagram. So in the origin, if we transform an operator at present, this is the action, okay? We can see that this is true just by looking at the structure of this operator. But if the operator is in the future, this means that it's conjugated by time, we need to move the C operator. It needs to be commuted with time. And every time we commute it with time, C moves to the right, okay? So this is why this point here in the middle, in the future, is displaced to the right. And in the past, is displaced to the left, okay? I hope this explanation was convincing. Okay, and you can do that with all the other generators. Okay. Also, of course, as you probably have guessed, we have two coordinates. Okay, so the plus and the minus. So these two generators transform the minus coordinate, as you can see here, right? Okay, we are transforming this coordinate. This coordinate. And the other two transform the plus coordinate. And of course, generators with C plus commutes with D minus and C minus and D minus dagger and C minus dagger. Okay. So yeah, so this basically reproduces the same structure than this. Okay, because by composing lots of transformations, of this type, remember that we can choose different origins X, okay? By choosing different origins, I can basically construct, any discrete F or G, okay? So with this, I'm justifying that this family of models has conformal, let's say a discrete version of conformal symmetry. Okay. You can also construct, this would be like a Lorentz transformation. This would be like a pure dilation transformation. But these are constructed by multiplying the previous generators. Okay, so this is just the particular case of Lorentz transformations. And now my plan is to move to tensor network states. Okay, I still have a bit of time. Okay, so now we are going to construct states. For instance, this is a state of 4 spins with the unitary of the dynamics. Okay, so this, if just I put the unitary with the 4 legs, the free 4 legs, I have a state of 4 spins. And with this, I can associate a geometry, a 2-dimensional geometry, where I substitute this gate by a cross. And then every time, if I want to move from this point to this point, I cross one black line. If I want to move from this point to this point, I cross 2 black lines. So this is the distance. How many black lines you cross is the distance. And why is the case? Because, okay, so maybe let me go later on. So the idea is that, let's consider now this tensor network state. I want that, let me consider now the reduced density matrix of these 5 spins. So what happens with these tensor networks is that the entropy of the reduced density matrix of 5 spins is equal to the length of the shortest path enclosing the 5 spins. Okay. And the entropy is 5 because we cross 1, 2, 3, 4, and 5 legs. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spins. But the entropy, despite having more spins for this particular state, is smaller, okay? Because we only close 2 legs. So the entropy is in units of logarithm of Q, okay? So this property that entanglement and geometry are equal is for is due to the fact that we are using dual unitaries, okay? So sorry. maybe in this case, so in this case, you can see, let's maybe prove one case. Okay, so I have a dual unitary. Okay, this is a four spin states. Now I'm going to construct, so this would be one ket. Okay, but now I want to construct the density matrix. So I'm going to put the bra. So this is complex conjugate. Maybe I put with a star of complex conjugate. And now I want the partial trace. The partial trace means that I need to contract, maybe I want the partial trace of these two spins. So this means that I need to trace the other Hilbert spaces. And now, because of dual unitarity, this is equal to this. Okay, and this is basically the maximal limit state of two qubits. Okay, so this is equal to the identity and over. Okay, so these two lines means identity for every spin. If you want, we can put identity for every spin. Okay, and the normalization. So it means, so what happens if the entanglement between these two spins and the rest, if the reduced state is the maximally mixed, it means that it's a maximally entangled state, right? So this partition that partitions these two spins with respect to the other is maximally entangled. And the entropy is going to be 2 units, okay, 2 identities, 2 times the logarithm of q, because each identity has a dimension q, okay? So this is one way to see it. But in general, it happens for more complicated states, okay? And now I'm going to finish, but before finishing, I want you to see how the dynamics works, okay? Sorry. No. Okay, sorry. Because it's very nice. So now let me take this state. This is just a state of 20 spins, okay? And I'm going to apply the evolution operator. And let's see how the state changes in time, okay?
Lluis,
yes?
Before you go, I don't want to get lost. So this evolution, this time evolution operator is exactly the same that you showed at the beginning with only one arrow per unitary. Is rephrased in, or is different?
So the one that had only one, yeah, it's the same, because the one that had only one arrow had 4 layers.
So it's a rewriting of that.
It's a rewriting, but it's the same. We have coarse grain space and time.
So then, but each one of these legs is squared in dimension.
Square the dimension of the original. But I invite you to just think now as maybe we can just forget about the original operator and think like each leg is just one spin, okay? So the reason
leg is like a one spin. Okay.
Yeah, and the reason I write these double arrows is because the way we constructed this, if I rotate it 180 degrees, it's the same tensor.
Mm-hmm.
Okay, so it's still the same. Okay, this arrow becomes this arrow, and this arrow becomes this arrow, but it looks the same. Okay.
Yeah. Okay. So
this is because the way we constructed. Yeah. So here, just the way we construct this, it has this symmetry. The swap is equal to the transpose, basically.
Right. Okay.
But now you can just now you can forget these gates and say, okay, I'm starting from scratch. This is my circuit, and the only thing is that I say that this is invariant under rotation of 180 degrees, and this is the rotation of this by 90 degrees plus complex conjugation. So if you have these two properties,
it's like saying it's invariant under transposition.
No, because it's not the same doing this than doing this. Okay.
Okay.
If you rotate, this spin goes to here, and if you do transposition, this spin goes here.
Okay.
Okay. So actually it's transposition and swap.
I see now. Right. Oh,
okay.
Thank you. Mm-hmm.
Thank you. Thank you for the question. So yeah, this is the time to see the dynamics. Okay, so how I'm going to, I don't know how to erase this, okay? Okay, no problem. So let me apply this evolution operator to this tensor network state. Let's do it. What I'm going to do is to apply this layer first and this second layer second, okay? So let me apply this layer and of course take into account that the zero side, zero spin is this one, okay? Okay, so I apply, so this is the tensor network state that we have here, and these gates are these gates, okay? So you see, this is what I said before of the corral, okay? The fence of the corral, but I just have flattened it, okay? Now, we can see that these two cancel with each other because one is the dagger of the other. These two cancel with each other. These two cancel with each other. This cancel, this cancel, this cancel. This cannot cancel with anything. Okay, so you end up with this tensor network state. Okay, so because this becomes the identity, so this spin moves here. Okay, you have this. Now we need to apply the second layer. No problem. I copy this state here, and I apply the second layer, the fence of the corral. Okay, so all these cancel, but these two don't cancel. So I get this different state. Okay, and now I could, so yeah, I call this, these are the T even would be the unitary, the tensor product of all these unitaries, and T odd would be the tensor product of these darker unitaries, okay? So here I apply only this, and here I apply the two layers, one that moves from here to here, and the second that moves from here to here. And you can keep doing so, and you find an orbit, okay? This is the orbit, and the orbit goes back to itself, okay? So it's like something like this. And this is what would happen in general relativity. So in general relativity, usually you usually have spaces without boundary, okay? Or the boundary is at infinitive. So usually you don't find this situation. This is a space, Euclidean space, or so that a time slice of space-time, if you want, that has finite volume and it has a fixed boundary, okay? And if you do that with general relativity, you get this type of oscillation. And what we have found here is a discrete version of this oscillation, okay? So yeah, maybe now I can move to anti-de Sitter. Should I, or should I stop here? Or...
Well, you have 10 minutes if you want. So I
okay,
think just
good.
consider.
Yeah, good. Okay, so now, so before we have studied this, the evolution of this state, but we could consider something that looks more like anti-de Sitter, okay, which is take a four-side spin and apply the dilation operator, which is defined like this, 3 times or any number of times. Okay, so this is an example where we apply it 3 times, but in general you want to apply it a large number of times. And then you construct this tensor network. Okay, and this is going to have the geometry of the hyperbolic plane. Okay, so for instance, if you calculate the entropy of some spins, you will see that the entropy grows logarithmically. So the shortest geodesic has logarithmic has a length logarithmic in this length, in the length of the boundary. This is also what you can see here, okay? And then you can interpret rho as the radial coordinate. Of course, you have to imagine this is the boundary, okay? So this has periodic boundary conditions. It's like the boundary. This is the radial coordinate, so this is the center. And we go outside. So the values of the radial coordinate is when we move at every cross-graining level. So one way to visualize this is by this, okay? So every disk, every section of a disk is the application of the dilation operator, okay? And this cap here, sorry. Yeah. And this would be this lead would be this thing, okay? So now we can take this state and evolve it in time, and we get this orbit, okay? And if we construct a superposition, so these are all the elements of this orbit, okay? So because we are applying the evolution operator, so when t is 0, we have this, which is equal to this, okay? Just written in a different way. T1, T2, T3, T4, T5, okay? So you have this eigenstate. Now, because this is the superposition of an orbit, it's an eigenstate of the dynamics, okay? And if we calculate the entropy of this eigenstate, we get these yellow dots. And the entropy of the conformal field theory would be the blue dots. The blue dots is the entropy given by the metric distance of anti-de Sitter. Okay, so we see that it's quite similar except in the center. But I believe this is because we are considering only 32 spins, okay? You would get, in the large scale limit, the initial region would be pretty similar. That's my guess. I mean, I don't have a proof yet. Okay. Another interesting thing is that, of course, here the entropy of these 4 spins versus the rest is 0, because here I'm not crossing any line. However, if I go here, I'm crossing 2 lines here and 2 lines here. Sorry, no, what I meant is these 4 spins, the entropy is 0. But if I take these 4 spins, the entropy is not 0. This is not nice because it means that the state is not translational invariant. Okay. However, if you construct the superposition of all the states, none of each is translational invariant. Okay. But if you construct the superposition, the resulting state has translational invariant entropy. So this is the entropy of 1 spin, 2 spins, 4 spins, 5 spins, okay? But it doesn't matter where you start counting spins, okay? So once you construct the superposition, the entropy of these 4 spins is the same as the entropy of these 4 spins, or these 4 spins. Okay, because when we do this superposition, it's like averaging over the different elements of the orbit. And you can see that this is very similar to this. It's just that it is rotated. So all together, it averages out the lack of translational invariance. Yeah, maybe now we can talk about this gravitational time dilation. Okay, so this is the anti-de Sitter's space for 64 spins, because every time we apply D, we double the number of spins. We start by 4, and we double it 4 times more. Then we have 64, okay? So 4 times 2 to the power of 4, 64. And these 4 Ds are just 1, 2, 3, 4, okay? And we can see it from different angles. And now I'm applying here this, okay? So this is 16 times the evolution operator. And we have seen before that when we apply the evolution operator, it commutes with D with the condition that the exponent is divided by 2, okay? So this is twice as fat as this. And this is twice as fat as this. And this is twice as fat as this. So we can see that time, as we go to the inside of the space, to the origin of the space, time contracts exponentially. This is exactly what tells us the anti-de Sitter metric, okay? So this is the radius, okay? And the cosinus of the cosinus is basically an exponential, okay? Because hyperbolic cosinus. And this, we would have a factor that multiplies the time coordinate and is exponential in the radius, okay? So this is precisely, so we find a discrete version of this exponential decay. 16 times, that moves to 4, to 8, to 4, to 2, to 1. And when we apply this state is an eigenstate, okay? So it's invariant. Okay, so this means that the 64 state also generates an orbit, okay, because it comes back to itself after 16 times. And something nice is that now what I've done is to take the single, the anti-de Sitter space, and instead of putting a tensor here, I'm connecting it with another one, okay? So this is like what people call a double-sided black hole, or a thermophile double state. Okay, and now if I apply the evolution operator to for people that is not familiar with holography, now what we have is two spin chains that evolve independently. So each one has periodic boundary conditions. Okay, but there isn't the state of the dynamics is independent in each spin chain, but the state is entangled, okay, as you can see via these legs. So this describes a double-sided black hole. And the take-home message is that with this formalism, we can see something that people is not able to see in standard holography, in ADS-CFT duality, anti-de Sitter conformal field theory duality. And this fact that we can see here is that when time evolves, if I apply 16 time steps at the boundaries, I can commute the evolution operator after every dilation isometry. This is the one dilation isometry, another, and another, okay? So what we see here is that the throat of the black hole, the wormhole, if you want, is growing linearly in time. Okay, this is something that you cannot see because the tools that the formalism doesn't give you access to the geometry behind the horizons. Okay, but here we can see if we apply more times the evolution operator, this will just keep growing in time. Okay, so you have to imagine that this is as I said, this has periodic boundary conditions. Therefore, this also has periodic boundary conditions. So this is like a cylinder. You can see that this leg connects with this leg. So it's like a cylinder. So maybe you can visualize it like this. This would be the top outside space. This is the throat. And I'm not drawing this lower side space. Okay, so if you only draw these things, after this gets more long after some time, you get this shape. Okay, and here you would have at the bottom you would have the other side of the funnel. Okay, so yeah, this is just to. I mean, honestly I don't know how much this is a toy model of quantum gravity, and I don't know how much it reproduces phenomena of quantum gravity. I just know that some features appear, okay, and maybe more will appear in the future if I have time to do more research. But yeah, I don't know up to which extent is toy, how toy is this toy model, okay? Yeah, also, if you put a particle in the middle, so until now we've been studying vacuum, empty de Sitter, okay? So now let me put a particle, which is inserting a tensor, a two-legged tensor here. So this is this circle here is a virtual spin chain, okay, that maps 4 spins to 8 spins. So this is a virtual spin chain of 8 sides. And in one of these 8 sides, let's say at side 0, I act a local operator, okay? So now if we do the same thing as before and I apply the evolution operator outside, when I commute it to this location, it only evolves this local operator to the future 2 time steps instead of 16. Okay, so it has this exponential shift, okay, that is typical of anti-de Sitter, okay? Anti-de Sitter is defined by this exponential shift of time, at least in these coordinates, okay? So yeah, this is just gravitational time dilation. Okay, so yeah, so maybe I should be concluding now. So with dual unitaries, we have created circuits with discrete conformal symmetry. Okay, this includes Lorentz transformation, scale transformations, but even more exotic transformations as well. Okay, because in 2 dimensions, the conformal group is very large, it's infinite dimensional, so on. Okay. I have introduced tensor-network state. I call them path integral tensor networks. I have not justified to you why I call them path integrals. Well, it doesn't matter. The main point is that we can interpret these tensor network states as discrete spatial geometries in 2 dimensions, in let's say, spatial geometries in 2+1 dimensions. And these geometries evolve in time when the spin chain evolves, okay? So if the evolution operator on the spin chains makes the geometry in the bulk, so the bulk has 1 spatial dimension extra than the spin chain. The spin chain is 1+1, and the bulk is 2+1. Of course, we don't, the 1, we cannot draw the 1. The 1 is the change, the different steps that we have, okay? So this is how holography works, by defining a quantum theory in the boundary of the bulk, okay? In our case, the spin chain. Sorry if you are not more familiar with holography. So with these circuits that have discrete conformal symmetry and these path integral tensor network states, we can play around and do finite radius discrete holography, which is these toy theories of quantum gravity. And it appears that I have shown to you that we observe, in some sense, the gravitational time dilation, the growth of the throat of the black hole, and this I haven't shown. Okay, this I have not shown. But yeah, it's just another thing that you can also see with this formalism. All these discrete geometries, these states in the boundary, obey the Ryu-Takianagi relationship between entanglement and geometry, but they provide more, because these tensor network states, they provide us with geometry beyond the horizon, while Ryu-Takianagi duality between entanglement and geometry does not. Okay. And yeah, well, let's ignore. That's all I wanted to say. Thank you.
Thank you very much, Lluis. It was really, for me, fascinating, really. So please go ahead. I mean, there are questions? I'm sure there are. I certainly have, but I want to.
Was it possible to understand something?
I have to. Well, it's suggestive. No, I mean, I personally don't claim to have understood all the details, but this all the music and the structure is very suggestive. So I have one one important question is, do you think you could add to this kind of matter that could support a wormhole, some energy violating matter that could make it traversable, or are you sure about the causal structure if this is traversable or not?
Yeah, this is not traversable, definitely.
It's not traversable. Yeah. Okay.
Yeah.
So
I don't know. I don't know if you can. I suppose that you can. Well, I don't know.
Usually, it involves a coupling between the boundaries, and it's a matter that couples both boundaries. Yeah. So this is
so it's this black hole is not formed. You have to just build a space-time that already has this wormhole. So it's not that you can start with a normal space-time and suddenly build a wormhole. That would not give you the wormhole that I show you. The wormhole that I'll show you just is the structure of the space-time you are in from the very beginning.
Right. Well, but typically what people do is they do a sudden coupling, and this makes a kind of a shock wave to go into the black hole. This shifts the horizon, then you can make it traversable instantaneously. For example, I don't know if this could be done here.
Yeah. Sorry. Yeah. So you know more than me. Yes, it would be interesting to see if this works here.
Yeah, it should work. I mean, it's very easy from other perspectives. It's kind of yeah. Another question I have: if these proposals, you have this tensor network that simulates ADS, I guess you have checked it satisfies all these inequalities. I mean, strong subadditivity, all this kind of other, not just Ritakayan, not just the entropy. Do they also, are they all satisfied, or this is
I haven't checked. That's an interesting question. Maybe they satisfy all the inequalities, maybe not all of them. I don't know. I mean, some things could be in the discrete, some things could be different. But I would expect that most of things would be the same as in standard field theory ADS CFD.
I see. Excellent. So seems that people is refraining, but I think it was a fantastic talk and a fantastic review, and I thank you very much, Lluis, and thank everybody for attending, and stay tuned. Yeah, stay tuned for the next seminars. And also, if anybody in the audience wants to contribute with his work, please just contact us. This is a public service, so we are happy to make everybody contribute and feel represented. Yeah. So until the next time. So goodbye, Lluis. Goodbye, everybody, and
goodbye.
Have a nice time, everybody. Goodbye. Ciao.
Bye.